I'd like to introduce our speaker, Professor Delphine Farmer. She received her PhD in 2006 from University of California, Berkeley. She then studied further at University of Colorado Boulder and then moved a little bit north to Fort Collins, where she is now a professor at Colorado State University. So welcome, and we look forward to your presentation.
Great, thank you, Bill. And I really appreciate the opportunity to be able to talk to you all about some of the work that my group's been doing. I'm an outdoor atmospheric chemist, so I study air quality and wildfire smoke and a lot of air pollution. But I recently became, over the last few years, realized that we spend a vast amount of time indoors, and this is where we're exposed to a lot of air pollution. And so I became quite fascinated by this problem. And so I'm going to talk to you about some of the work that my group has been doing. And we've been working with a variety of scientists across the US and Canada, thinking about cooking, particles, cleaning, and their health effects. And so we're going to explore, I'll tell you a little bit about indoor air quality and sort of some of the fundamentals of why we should be worried about it or thinking about it. Then I'm going to tell you a little bit about this crazy study we did in Texas a couple years ago. And then I'm going to tell you a little bit about cleaners and cooking emissions, and we'll end up with a couple of slides about things that you might be able to do or think about in terms of controlling the air quality in your home, which has only become more relevant as we all spend more time indoors, particularly in our own homes during this pandemic. So overall, though, what I really hope you get out of this talk is that homes and buildings are incredible chemical reactors. We are all living in a chemistry experiment, and there are gases and there are particles that get into the air, and these we breathe in, and they can do all sorts of interesting reactions. Some of them we should be worried about. Many of those reactions we shouldn't be worried about. But this is a chemistry experiment that we're currently breathing. So why should we care about this? So we currently spend about 90% of our time indoors. And to put this into perspective, Rich Corsi, who's the sort of a very well-known figure in indoor air quality, pointed out that we could think about this in terms of the average lifespan of a human of one of us adults in the United States. And there was this beautiful study done a few years ago from the Lawrence Berkeley National Labs in California, and they called up very large numbers of people across the United States and started to figure out how much time people actually spend doing different activities. And what they found is we spend 90% of our time in buildings, but we can divide it up a little bit further. So using the results of that survey, Rich Corsi pointed out that if our average life expectancy is 79 years, it turns out that the average North American will spend 69 years indoors. Of that, well, we will spend 54 years at home in our residences, not always the same residence, but 54 years at home. You will spend 26 years of your life in bed on average, 4.3 years in vehicles, and a measly little 6 years of your average life, if you are an average United States adult, you will spend a measly 6 years outside. So these are kind of mind-blowing statistics when you first hear them. And I mean, obviously, time spent at home in a pandemic has changed some of these numbers a little bit. But overall, this is the average. These are the statistics. And the thing that I found incredible about this field when I first started thinking about it is that most of our air quality and health research has actually focused on outdoor air pollution. And there are great reasons for that. One of which is that we can regulate outdoor air pollution sources. It's very hard to regulate people's homes, nor should we, I think. But there's been very, very little research on understanding where we spend the vast majority of our life. We can think about this in a few different perspectives, and you can think about different kinds of buildings. Again, we spend the vast majority of our time inside buildings or vehicles. And some of those are homes, and you can look around your house and you can look around other people's houses, especially now we're all on Zoom, and you can think about all of these different surfaces and sources and different things in different buildings, and realize that there might be some big differences from building to building and from house to house and apartment to standalone homes. We can also think about other indoor environments, so offices, workspaces, hospitals, schools, and all of those are quite distinct as well. But fundamentally, what we're here to talk about today is what is in the air that we breathe. And you can think about this from a few different perspectives. So we can think about the gases that get emitted, and you know about these. When you crack open a lemon or a lime when you're cooking, or when you clean with one of those really strong pine scented cleaners, what you're smelling are gases, are volatile organic compounds. Now, most of the air that we breathe is made up of nitrogen, and then it's about a quarter of it is oxygen. That's really good. We also have some carbon monoxide and carbon dioxide. Those are less good, but they're, and if you have too high a carbon dioxide, too high a CO2 level inside your home, it actually starts to impact your capacity to think. It impacts your cognitive ability. And it turns out that quite often in closed buildings and school classrooms, interestingly enough, those CO2 levels can actually get to be quite high and problematic for cognitive capacity. You also, it turns out, can smell things like the oils from the turkey that you might have roasted at Christmas or Thanksgiving. You'll smell those citrus associated organic compounds. Are called limonene is one of them. So all these gases. But then you also have particles in the air. And you know about these particles if you have lit a candle and you see that smoke. What you are seeing there are small liquids or solids that are suspended in the air. They have some similarities to smog, wildfire emissions, and cooking. They all actually chemically have some strong similarities. And we can think about these particles for a moment. They all come in different sizes. And those different sizes depend a bit on their sources. So right down at the really small end, you'll get viruses, actually, and small bacteria. But around a few hundred nanometers in size, you'll see wildfire smoke. And those are actually the same sizes of particles we worry about wildfire smoke, are the same sizes that we actually worry about people exhaling and containing viral particles or other pathogens. And then as you get larger particles, then you get up to things like dust, which you also see in your home, and brings along its whole own world of chemistry. So we can think about these different types of particles, but the ones that we're going to think about in the indoor environment are really the sizes. They're a few hundred nanometers, so that's wildfire smoke, that's urban smog. We might want to think a little bit about respiratory droplets, what we breathe out right now. But we have these particles, they're in our air, and the reason we worry about them is that when you breathe, those particles get into your lungs, and then they can interact with the tissues of your lungs. So things like pathogens can pass through into your organs, into your lungs, and into your bloodstream, and then multiply. You can also think about particles that carry carcinogens. So cigarette smoke, we know is harmful to you, but wildfire smoke chemically isn't that different. And so we can think about those carcinogens, those toxins, they can then pass into your system. So you can breathe in those gases, or you can breathe in those particles. So how do we think about indoor chemistry? There are a lot of different approaches. We could think about looking at many different buildings. We could try and send sensors to every household in Fairbanks, and that would be quite the effort. But because it would be so hard, it would be we would only be able to measure one or two things in the air. So one approach to looking at indoor air quality is to survey houses or buildings, and to look at large numbers of them. The other way we can think about indoor chemistry is to think about one house, and we can think about it in detail. And as a chemist, that approach has really appealed to me, because it means that we get to think about the actual chemical processes occurring in a building. And so I had the opportunity a couple of years ago to work with some colleagues and some friends from a variety of different universities. And what we decided to do was think about indoor chemistry by using one house. We called it a test house. I'll show you a picture in a moment. And what we did is we took a huge number of chemical instruments and we put them inside the house or around the house. And then we did controlled perturbations. And when I say a perturbation, I merely mean that we gave the house a kick. And by a kick, I mean a chemical kick. So we cooked a stir fry, or we mopped the floors, or we sent a whole pile of graduate students into one house, and we saw what happened. How did the chemistry respond? How did the air in the house respond? So we called this experiment Home Chem. That's house observations of microbial and environmental chemistry. And so with this project, we went down to the University of Texas at Austin, and you can see this little tiny, very standard representative prefab house that was in the middle of the structural engineering facility. So we were surrounded by concrete blocks, and it was mildly post-apocalyptic. But we had a month in June in Austin, so it was quite hot and humid. And the goal of this study was to characterize aerosol and gas-based chemistry during cooking, cleaning, and occupancy. So everyday events, how do everyday activities in your home change the chemistry? So that was the front of house. Back of the house looked a little bit different. We actually got a whole pile of portable offices that we set up behind the house, connected into the house air with tubing, and we pulled air from the house into instruments that we had inside all of these trailers and trucks around the back of the house. Inside the house looked a little bit like this. If you peered into the window, you would see a group of researchers, for example, just sitting down working on their computers. And in this experiment, what we were doing was just looking at the emissions of humans, of these students. And so they were collecting data, and then we were just looking at what they were breathing out and what was coming off of their skin and how that was reacting. So this was the experiment. It was an incredibly collaborative project. We had a huge group of undergraduates, graduate students, researchers, professors from all across the US and Canada, and a huge number of institutions. One of these was actually Pete DiCarlo, who's going to come and talk in this series next month. So I'm sure he'll share some of the results that we got from this experiment. So the idea behind Home Chem is that we did a couple different types of experiments. One is where we would do one activity over and over and over again. So we would mop the floor, and then we would watch what happened, and then we would mop the floor again. We would watch what happened. So we did a lot of mopping, and we made a lot of stir fries. And then we also did experiments where we took all of these activities and we put them together. We called that a layered experiment. So we would layer cleaning and cooking and occupancy all on top of each other like you do in a regular day in your life. Except probably with more cleaning than most people do. So we had this really busy month where we did all these different types of cooking, all these different types of cleaning. And what we can do now is look at all this data and use it to tell us about the chemistry inside our homes. So I'm going to walk you through one or two really neat examples of what we saw, and then we'll talk about what this means for you. So here's an example of one of those layered days. So what we did is this is midnight to midnight on that bottom x-axis. And then each of these little traces is a different type of concentration of something that we observed. So you can think about it as we had people show up in the morning, around 7 in the morning. And so as soon as people walked into that house, we could see that very bottom trace, that carbon dioxide trace, starts to go up. And that's actually because humans are breathing and we breathe out CO2. But then you see we would do some cooking and we would turn on the gas stove, and then that would release a huge amount of carbon dioxide. So we actually got really crazy levels of carbon dioxide, and it turns out these are quite normal for inside homes, but they're quite high. We saw that ozone, which is an air pollutant that we really worry about in the summer in urban environments and cities, that was actually really low. Ozone was far lower inside than it ever was outside, so that was good. Same, some of these other pollutants, nitrogen oxides, those come from lightning, vehicle exhaust. It turns out that turning on your gas stove also releases a huge amount of those air pollutants. So we would see those every time we cooked. But then we saw some other sort of interesting compounds. So we saw acetone, which some of you might know as nail polish remover, and isoprene, which comes out of plants. We actually saw those just when people walked into the building. And that's because your metabolic processes, so your body just operating and doing its biochemistry, actually releases acetone and isoprene in your breath. So you breathe your breath. So you breathe out these volatile organic compounds. It turns out then that when you do things like you cook, if you cut into anything with citrus, you'll get a huge spike in the air of limonene. You know that because you can smell that citrus scent. And then it also turns out that we can have some less benign, more toxic compounds. And if you clean with bleach, which I'll talk about in a little detail in a moment, it turns out that you can create all sorts of interesting chemistry. And that releases chlorinated or halogenated compounds into the air. So what you should really see from this picture is that the chemistry in the air inside your home is really dynamic. The concentrations change really rapidly every time you do something. And so that might be disconcerting, but it's actually really cool because it means that you can control the chemistry experiment. You get to control the air inside your home. So let's think about this in a little bit more detail. So how does indoor air contrast to the outdoor air? Now, I know that Austin, Texas in the summer is very, very different from Fairbanks, Alaska in the winter, but we can still get we can still see a few parallels. So the first thing to know is that volatile organic compounds, VOCs, they are really, really high indoors. And it turns out that what happens is every time you cook or clean or even just breathe, you're releasing these volatiles. They are not, you'll hear sometimes indoor air quality people talk about VOCs as being really bad for you. They're actually not. The majority of them are perfectly fine to breathe. But then they get sort of stuck on the sides of the walls in your house, and then they slowly come back off. So it's always kind of interesting to think that you are breathing air that was influenced by whatever you did yesterday, last week, even a year or two ago. That can all influence the air that you're breathing now. So we see these really high concentrations of things we call monoterpenes, so pinene and limonene, the same things that make pine forests smell like pine forests and that make lemons and limes smell like lemons and limes. So, so you get these really high concentrations indoors. That's not necessarily bad. We also find that a lot of air pollutants indoors are much, much lower in concentration than they are outdoors. That's a really good thing. So particle concentrations are in general much lower inside than they are outside, unless you are cooking or burning stuff. Candles, wood fireplaces, those are all great ways to make particles. Anytime you burn something, whether it's natural gas or wood, you're gonna make particles. But if you're not doing any of those activities, then from a particle perspective, the air inside your home is actually really, really clean. So we can compare what we did in Texas was compare indoor concentrations, and you see that on the left-hand figure, you can see these blue dots, and they're much lower, about half the height of those black dots, which are the outside concentration. And then you can see that if you look over on the right, even the act of making a piece of toast, you release a whole pile of particles into your house, let alone if you are going to make some eggs and sausage or cook a stir fry. So how does indoor air contrast to outdoor air? We have high concentrations of VOCs. That's fine. We have very rapid changes in concentration. That's kind of interesting. We also have very low amounts of ozone. We don't have very much light. So the air quality it shouldn't be too bad unless you start doing things like cooking. So as a chemist, that's sort of interesting, but wasn't super exciting until we started to think about some of the types of cleaning. And so I'm going to take a moment and tell you a little bit about bleach cleaning. It's become quite popular recently because bleach is a very strong disinfectant. So it's one way to clean surfaces from things like viruses and bacteria, and the coronavirus certainly works for that. But it also turns out that bleach solution, when you mop a floor or wipe a surface, you get this little watery layer. And that layer allows all sorts of chemistry to occur. And the bleach reacts in that little layer of water, and then it gets into the air, and then it reacts and does chemistry in the air. And that chemistry, it turns out, is rather toxic. So chlorine bleach cleaning, as I say, it's become really popular. In the course of a couple weeks last March, the number of calls to the US Poison Control Center in terms of disinfectant exposures and bleach use just skyrocketed. And there's a large number of interesting cases. Not going to go into them. What I want to show is the data. So what you're seeing here are 3 different examples of mopping the floor with bleach. And this is just mopping according to manufacturer instructions in an actually relatively clean test house. This one in Texas. And what we saw with some of our really fancy instruments was actually quite impressive. So we saw hypochlorous acid, and we expect that because that's a key ingredient in bleach. But then we also saw molecular chlorine, which is a really toxic gas. It was used in chemical warfare in World War I. We also saw nitrile chloride, that's ClNO2 on the bottom left. This was fascinating because the concentrations were really high. And that's a kind of compound that we might expect to see in a city that's right next to the ocean, but we didn't expect to see it in a house. So what this told us was that there was a huge amount of chemistry. And I'm going to cut out all the chemistry and sort of show you one figure. And this figure on the left, what you should really be seeing is that there's a huge number of chemical reactions. We were able to sort of trace all of these reactions. And we found that the bleach solution, when you apply it, or if you, and I really hope you don't, mist it in the air, which a lot of dentists' offices are doing for some terrible reason right now, what happens is that bleach solution causes chemistry that creates a huge array of toxic products. All of these, we call them chloramines, so NHCl2 and Cl3, those sorts of compounds, they're actually quite toxic. And then you can do even more chemistry in the air and create a large number of chlorinated and organic chlorinated compounds that we know are carcinogenic or toxic in other ways. So it turns out that there's all this chemistry occurring in all of these different phases in the air and in your bleach solution, and that creates an array of toxic compounds. So mopping chemistry turns out to be quite interesting, and it turns out that the chemistry doesn't just occur in the mopping solution on the surface. It turns out that it happens in the air and then on all the other surfaces in your room. So what that does, what that chemistry does, is it converts some of those volatile organic compounds, like the ones you just naturally breathe out, it converts them to quite toxic compounds. So bleach cleaning, you shouldn't just worry about the bleach itself and wearing gloves, which you should certainly do, but you also want to start thinking about all of what it's creating in the air. And in general, I would recommend against using it. And if you do have to use it, I'll talk to you at the end a little bit about what you might want to do. Okay, so last couple notes, don't worry, we're almost done here, is what happens when you cook. And so even though it was June in Austin, Texas, so not the type of weather I normally associate with Thanksgiving, we did decide to look at the chemistry of cooking events, and what more extreme event is there than a Thanksgiving dinner? And so we actually decided to cook in June. We sourced a couple turkeys and we cooked a full Thanksgiving dinner a couple times. And then of course we ate it, but we also looked at the chemistry. And it turns out that the chemistry was quite fascinating. So these are some pictures from the meals that we cooked in case you haven't had dinner yet. It was quite delicious. But all of these different components, the turkey, the stuffing, the roast Brussels sprouts, the roast carrots, the pies, the cranberry sauce, every single one of those components, you know it does chemistry because you know that it smells really good. Not necessarily bad chemistry, but you know it just does chemistry. So when we look at it, it turns out to be quite fascinating. And it turns out that you get a huge number of different kinds of compounds all coming out. Of course, different compounds associated with different cooking types, different activities. So whether you are cooking cranberry sauce or you are roasting vegetables. But one thing that was fascinating is how similar cooking, especially roasting, was to wildfire smoke. Chemically, they're actually, some of those aspects are quite similar. A couple of other interesting tidbits is that it turns out that when you cook your turkey, the oils that are from the turkey that contain things like cholesterol become particles in the atmosphere, and then you breathe them inside the kitchen. So you might think you're a vegetarian, but if there's a cookie turking, you're certainly breathing it in, which makes for an interesting experience. But one thing we saw this sort of huge array of molecules, we had all these different instruments, and they all told us about all these different molecules. And it took us a little while to think about whether or not these were bad for you. And I mean, a lot of them just smell good, but do they do anything for your health? And so one way to look at this is to think about the health effects of each of these individual compounds that we measured. So traditionally, household air pollution is thought about by scientists as chronic exposure, but that's really driven by research in the developing world. So if you think about people who have one room to live in and a wood-fired stove that is constantly going, that's certainly chronic exposure. But in most houses in North America or the developed world, we don't cook all the time, even in the midst of stay-at-home orders here in Colorado. So we can start thinking about, I thought we should start thinking about health effects of all of these different compounds that we measured when we cooked Thanksgiving dinner, when we cooked their stir fry. We could think about them in terms of their acute effects. And it turns out that the EPA and the California Air Resources Board and a few other organizations have all got toxicologists who thought about what levels of different compounds are safe or dangerous. And so when we looked at how our levels that we measured in our admittedly only one house in Austin in the summer, we could compare the levels of all of these different compounds that we saw to levels that are thresholds that are known to be toxic. And so that's what this figure shows on the right. I'm going to walk you through it for a moment. So on the bottom, you see different activities. We cook a stir fry, or we make breakfast, or we cook Thanksgiving dinner, or we just leave the house and don't do anything and we watch what the air in the house is. That's that background measurement. And what you should see here is what we were really worried about is anytime the ratio of the concentration that we measured to that threshold toxic concentration, we worry about when that reaches 1 and when it goes over 1. And the great news is that for almost nothing were the levels of air pollutants above 1. When we start to add them up, maybe Thanksgiving starts to be a bit of a problem, but even then it's not too bad. But what's fascinating is that there was one molecule called acrolein, and I have its chemical structure on here because I am a chemist and I can only think about chemical structures like this, but that one molecule, you see it in those red blocks, and you can look over and you can see that ratio concentration, that ratio is over 1, under almost any circumstance. So that's one molecule that we did find that often exceeds a health threshold. And so that suggests that cooking in particular is a really strong source of acrolein. And so that started to tell us that maybe we should start thinking about ventilating when you cook, and we should start being a little concerned about that air. But most of the molecules that you're making are at low levels. So now that we thought about it, the question is, what can you do? What can you do about things like these high levels of acrolein? So the first thing that you can think about is ventilate. And if you're cooking, I always think about it as everyone at home automatically knows what they should do to ventilate, because you have probably, like me, burnt food to the pan at some point. And so you have smelt that smoke, you burnt that toast, you know what that burnt cooked food scent is. And so whatever you do in that circumstance, whether it's generate a cross breeze by opening a couple windows, turning on the fan in your kitchen, or turning on the fan in the bathroom and opening the door, those different activities are amazing ways to ventilate the house. So what I do now, what I recommend other people do, is to consider every time you cook, to always think of it as though you're burning something. So whatever it is that you would do to get rid of that burned smoke smell, that's what you should do in terms of your home. So what else can you do? So ventilate to remove air pollution, so windows, Bathroom fans, especially in Alaska, I mentioned you don't want to be opening your windows when it's really cold out or when there's wildfire smoke. Kitchen hoods are great. But the other thing you can do is you can think about bringing in clean air. So that's your HVAC system. So your heating and air conditioning system. Often they have filters that you can put in them. Those are really important. People often forget to change those filters, but that's how you get clean air into your home. So you can bring in clean air, and that's great. And then you can also, if you don't want to be opening windows and you don't have an HVAC system that can really bring in lots of clean air, you can clean the air that you have. And so you can do that the expensive way, which is buying a personal air purifier that has a HEPA filter. Those things are amazing. But you can do it for almost just as good a result, a really, really cheap way, and that is to get a box fan and buy one of those filters that you should be putting into your HVAC system. And you can put that on the box fan, and it turns out that this works almost as well as these really expensive personal air purifiers. So there are things that you can do to improve your air quality. Okay, last slide. What shouldn't you do to improve your air quality? There are a couple things that are important to think about. First off, don't bring pollution into your home. So I would turn off all the sources. If you can avoid using gas stoves, great. If you're like me and you bought a house that already had gas stove in it, turn on the vent hood over the stove. Avoid things like candles. Anything that burns is a really great way to create air pollution. Air fresheners, essential oils, those they might make your house smell nice, but they're all bringing in compounds that can react and create chemistry and not do good things for your air quality. And then of course, there's the chemicals that you bring into your home, whether that's pesticides or harsh cleaning products. All of those, remember, those concentrations are really high in the air, and that means that all of those organic molecules stick to the paint and the doors and the furnishings in your carpet in your home. And so trying to not bring in toxic compounds is another really great tip. Finally, don't bring chemistry into your home is my general thought. Try not to bring in the bleach or the peroxide unless you're cleaning for a medical purpose. Try to avoid those for general purpose cleaning. Whatever you do, don't buy these fancy and expensive cleaners that bring in ozone. They're hydroxyl radical generators. You can buy ion generators. You can add UV light into your homes. All of these are actually quite dangerous and cause a lot of chemistry that's really harmful. So those are some do's and don'ts in terms of making your improving the air quality in your house. So here's my summary. Your house is a chemistry experiment, but that's cool because you can control it. There are a lot of VOCs in the air. You breathe them, you cook with them, you clean with them. That's fine, as long as you don't do things like react them with bleach or ozone generators, then they'll stay pretty good. A lot of traditional outdoor air pollutants like ozone and particles are often lower inside, so that's great. Cleaning causes chemistry. And so finally, I just want to point out that cooking produces a lot of molecules. So at the end of the day, try not to burn stuff and ventilate and ventilate and ventilate. Try to bring in clean air into your house. And that's what I've got. So I'm happy to take any questions, comments, talk about any of these aspects in a little more detail. So Bill, over to you.
Yeah, well, thanks so much, Delphine, for the talk. It was really exciting. And I'm seeing a number of comments coming in, both from the Zoom, and I think a few are coming from Facebook too. So Kelly, do you want to read out a question that we got in there?
Hi, sure. We have one question from a viewer that's asking, what was the air leakage rate of the test house?
Yeah, so it was, I'm not gonna put numbers into it, but I will tell you that we had a building scientist at Villanova Slack who was amazing, who ran the house. That is not something chemists should do. Building engineers need to do that. And he tweaked the house and the leakage rate and the air exchange rates to sit right in the average for North American households. So we had an air exchange rate that was about a half per hour. And so that set us in the absolute norm for houses. So the leakage rate was neither high nor low.
And it was natural leakage. It wasn't like a
Yeah.
doing that.
We were a little worried because we had to put holes in the wall for all our tubing to send air into our mass spectrometers and those trailers in the back of the house. And so we were worried that we'd really change the leakage rate in the house. And so we did a lot of tests, and it turns out that it takes a lot to make a house extra leaky when it's already kind of old. So.
Okay. Yeah, so a bunch more questions coming in, Kelly.
We've got one. If the outdoor air quality is worse than indoors, then cooking outside is not better, correct?
So good question. It depends on who's cooking and who you're worried about. So if you have kids with asthma, you should probably leave them inside and go cook outside. And that would be really good for them. Not so good for you, but sacrifices must be made. But if you are, if you're in a vulnerable population, if you're sensitive to air pollution, any history of cardiorespiratory disease, then you probably do want to be cooking at home, but with your range hood on if the air pollution is bad outside. So wildfire smoke events, which we certainly have had some extreme ones here in Colorado and the Front Range over the last couple of summers, this year being terrible in Fort Collins. When the air quality is, when you see it hazy outside, or you get those air quality alerts, then you definitely are better off being indoors and cooking indoors and doing what you can to minimize the particle production indoors than you are being in that quite polluted outdoor environment. So I would always try to avoid being outdoors when you have those heavy air pollution events.
Awesome. I saw on some of your slides there that the natural cleaners had some pretty big spikes of maybe VOCs. Could you compare natural cleaners to like chemical cleaners, bleaches, and talk about relative merits?
So it was really interesting when we first started seeing all the data. We were sort of surprised. We had some of these sort of citrus scented natural products that you just buy in the grocery store, and we saw these really high levels of VOCs and all these different compounds. And at first that made me quite skeptical of them until we started looking at what those compounds were. And it turns out they were compounds like limonene and pinene that really aren't toxic. And so what they weren't accompanied by were any of these toxic halogenated compounds or these oxygenated compounds that can react with your lung tissue. So while those sort of natural product cleaners can certainly smell strong, they weren't doing any bad chemistry. And so when we went and looked into those health effects, and I've got lots of data, but I'm not going to show you those health effects of cleaners, it turns out that the natural product cleaners or the pine scented cleaners really are not impacting the health of the air that you're breathing. In contrast, things like bleach cleaning it can be quite strong. Ammonia, of course, and vinegar actually can get some really high levels. And so when you know that the smell isn't great, then that's a problem. I would encourage you to avoid those harsher chemical cleaners.
Kelly, another question from one of the streams?
We've got kind of a two-part question here. How well do air purifiers work, and do they remove gases from cleaning products?
Yeah, great question. So those air cleaners, those simple ones that have a filter, whether it's a box fan, and I can even go back a slide and show you. So these filters that have a box fan and a HEPA filter, or where you buy a HEPA filter with a fan in it, those work really, really well to remove particles. They can do an okay job with some of those cleaning products. Some of the bleach compounds will actually stick to those filter surfaces. The ones that you buy may also come with an activated charcoal trap, and those can work pretty well if you only clean occasionally. They get kind of used up relatively quickly though. So you can clean out those organic gases, those compounds that you're breathing that aren't particles, that they're just gases floating around in the air, but they're not very effective. So if you're cleaning with something like a bleach or a peroxide or a harsh cleaner, something where you're worried about the gases, then you want to go with ventilation as your strategy. So I always think of trying to use lots of different strategies to kind of clean your air, much like you would in most other scenarios. Just vacuuming does not make for a clean and tidy house. You kind of have to do a lot of different things. Same idea with cleaning. If you can use a few different approaches, so use a filter approach, but also ventilate, then you're doing a much better deal. You have a better approach for dealing with problems.
Great.
Another question. We've got somebody who's curious about indoor swimming pools where the air is stung with chlorine. Is that toxic to your health too?
Yeah, and that one was distressing for me to find out. But yes, it turns out that chlorinated swimming pools have some pretty high levels of toxic chlorinated compounds. So I think there you want to think about whether or not, short-term exposures to those, that's not necessarily going to have a huge health impact. There's no documented research. But for people who are spending huge amounts of time in those environments, then it's worth thinking about whether or not you have a history of cardiorespiratory disease or asthma, and then it might be a problem to really think about.
Okay, and what do different cooking surfaces such as cast iron or nonstick do to chemistry?
Yeah, we actually looked at that and we thought we were going to find some really interesting results. And it turns out that it really doesn't make much of a difference at all. So your cooking pan itself doesn't really matter. But the way you cook, whether it's an electric plate versus a electric stovetop versus a gas stovetop, that makes a big difference. Electric stovetops produce a lot less air pollution inside your home.
I see a question about, what about all the cleaners that we use in the schools to sanitize, like wipes?
Yeah, so that's an interesting one. And it's, you always, right now you have to balance competing interests, right? We're worried about transmission of coronavirus. But it turns out that surfaces are a pretty minor method for most transmission, but I also know that small children are a bit of a different ballgame from in terms of transmission and cleanliness of surfaces. But those wipes turn out to not do a lot of air chemistry. But a lot of the other cleaning products that are being used in schools and in commercial buildings actually are pretty harsh. So a lot of schools are beginning to use heavy bleach. Peroxide is becoming quite popular for surfaces. Those are things where they'll certainly, they will cause problems to whoever's breathing them in. So that's actually more of a concern for the janitorial staff, because a lot of those cleaners are being applied after kids have left the school for the day. So it's a concern for the workers. It's less of a concern for the children, as the next day, most of that stuff in the air is going to be cleared out. But if those products are being used while there are, in particular, children who are quite vulnerable to, in terms of their lung tissues, if those products are being used then that's a problem. And so I'm quite wary of overuse and very, very heavy use of powerful disinfectants. So I think it's something to be cautious about.
Kelly, another question?
After how many years is it recommended to replace carpets in your house? I'm not sure if this is kind of relevant, but the person's thinking about holding dust and dirt and things inside carpet.
Yeah, so it's interesting. So you can clean carpets, and that works well. Just ventilate while you're cleaning. But the reason to change, one of the reasons from a chemistry perspective to change carpets, well, there are really two. So one is mold. And that's an instantaneous reason to change carpets, because once that settles in, there's nothing you can do about it. But the other reason is if you have had like a cigarette smoker in the house, then it turns out that cigarette smoke breathes, people exhale and the smoke comes out inside the home. It settles into the carpet. And then on a time scale of days, months, even years. Actually the nicotine and some of the other compounds in that cigarette smoke will do chemical reactions on the surfaces of the carpet fibers and create really toxic products. And then if you have children coming along, spending a lot of time near the floor, or even those toxic molecules will then evaporate into the air in the home, that can cause a problem. So I would leave it to sort of more materials degradation and what you know about wear and tear on carpets in terms of replacement, with the exception that if you have someone who's has smoked cigarettes inside a home, the chemical effects of that and the toxins that those will produce will last for years, if not decades.
So a nice question about your recommendation on kitchen fans. So how long should you leave it on after you're done cooking?
Yeah, so every home's a bit different. They look different, right? You know that. So I would do the burnt toast test, right? So if you burn something or you cook something that smells really strong, like sort of fish or a curry, then you know how long you need to leave the fan on until that smell dissipates. However long that is in your house, that's how long you probably want to be leaving it on. So do the experiment. Cook a really strongly scented food and then see how long it takes to clear out the air.
Cool. Kelly, other questions you're seeing?
Let's see. So this may have already been covered, but how does indoor air quality compare to nearby outdoor air quality?
Yeah, so overall, most of the classic air pollutants, so the things we think about in terms of particles and ozone, the components of smog, usually those are much better indoors than they are outdoors, unless you do certain activities like cooking or burning stuff, so lots of candles lit in the home. If you do things like that, then your indoor air quality might compete or be worse than outdoor air quality. But in general, if you're just sitting, reading, watching TV, then the air inside your home is according to those classic air pollutants, better. On the flip side, I'll say that there's one of the things we learned with the home chem experiment, and you saw that one of those slides I showed with acrolein and some of these other compounds, there are a lot of molecules inside the home that are coming off of building materials that we as scientists just don't know how bad they are. And so we don't know if we should be considering them as air pollutants. So in terms of the air pollutants that we do know about, which are the only ones that really keep me up at night, in terms of those ones, you're actually better off inside your house than outside. Unless you're doing some extreme cooking or burning or cleaning events. But past that, we have a lot to learn.
You mentioned the electric and gas ranges. Could you kind of compare how different those are as sources?
Yeah, orders of magnitude. So let me see if I can go back to one of the first slides in my deck where I showed. This will take a moment. I showed what a whole lot of those different gases that we measured. Here we go. What they look like. And so if you look. On the right-hand side, you've got a figure. And again, we have that midnight to midnight on one sort of day of experiments. And you can look, the first set of traces up from the bottom in black and gray are NO and NO2. And so those are the NOx pollutants. We worry about them from the tailpipe of your car. Key ingredient of urban smog. But these levels that we got to were really high, hundreds of parts per billion. And those are levels where there are negative health effects from those nitrogen oxides. Those molecules came purely from the gas stove. So when we used an electric range hood, we did not have any of those nitrogen oxides. So in terms of what's better, there's no question you have fewer pollutants by a long shot with electric stoves, and that's just always that's always going to be the case. Unfortunately.
So maybe we'll do a last question or two, and then I just want to say to the people, lots of great questions coming in, and we're going to try to answer some of these. We're going to put up something on the FairAir website, an event talking about this event. And in that news article, we'll try and answer a couple more of these questions that we see coming in. So maybe Kelly, you want to pick a last one?
Sure. How about we have somebody who's curious about latest reviews of indoor PM 2.5 filtration systems for residential use and how that individual cost compares to collectively pooling our resources to mitigate the sources.
Yeah, yeah, that's a great question. So overall, if you've done everything that you can do, you've decided not to burn candles, and you've decided to not have your gas stove or always use your hood when you cook, then the air, the particles in the air in your home that you're breathing are directly related to the number of particles outside, and that's just that they leak into the house. And so at that point, what really matters is the quality of the air outside. And there are sources we know about. If you live near a road, a busy road, then we know that vehicle exhaust puts out particles. And that's a really interesting ethics question and is an interesting economics question. But I think that we look at things that we know that particulate matter, those particles outside, are correlated to negative health effects. They're correlated to hospital visits, they're correlated to asthma rates, and they're correlated to cardiorespiratory disease. And so because we know that, it seems like it's in everyone's best interest to try and reduce those particulate matter levels that we can. And of course, one of the unfortunate things, and I think Fairbanks has one of the, also has the same effect that we have in Colorado of wildfires. And to an extent, there's not a lot we can do to control that, although there are larger scale issues of climate and how that's impacting wildfire levels. But I do think about the things that we can control. And we can control those emissions from vehicle exhaust. And those do have a direct impact on indoor air quality. So I think it's worth talking to the people who set policy, because that impacts our health and the health of our children.